Good morning. Welcome to the webinar series on managing drought in the Southern Plains. I'm Mark Schaefer with the Oklahoma Climate Survey and Southern Climate Impacts Planning Program, and I will be moderator for today's webinar. We will be joined by Brian Fuchs from the National Drought Mitigation Center, Mark Svoboda and Brian Wardlow from the National Drought Mitigation Center, Martha Anderson from USDA-Agricultural Research Station, and Pat Ganan, Missouri State Climatologist. Margaret Boone, SCIP Program Manager, is managing the webinar. Before continuing, I'd like to remind anyone calling in to please mute your phones, either using the mute button or *6. In addition to the presenters, several state climatologists are on the line, including Dave Dubois from New Mexico, Gary McManus from Oklahoma, and John Nielsen-Gammon from Texas. I would also like to recognize the support of those who made this webinar series possible. Chad McNutt with the National Integrated Drought Information System, or NIDIS, David Brown, NOAA Regional Climate Services Director for the Southern Region, and Mike Hayes with the National Drought Mitigation Center. I'd like to briefly recap the goals of this seminar series. We planned these in order to improve communication across our region to help those agencies and organizations that are managing aspects of the drought. We want to ensure that the information presented is timely and relevant. Our presenters will include a combination of scientists, state climatologists, and resource managers. We are always looking for potential presenters, so if you have expertise in a particular area and would like to be a presenter, or would like to recommend others we should ask, please contact us. These webinars are an ongoing series that will occur on the second and fourth Thursdays of each month. Our next webinar will be November 10th. Each webinar will include an update from the Drought Monitor authors and state climatologists. Each will have a discussion topic based on the topics of greatest interest, as indicated by the poll subject to the availability of presenters. You will now see on your screen a poll for future topics. Please cast your vote for the topic you would like to see next. We have begun lining up presenters on several of the topics indicated from previous webinar polls and can confirm that cattle and livestock will be the focus for the December 8th webinar. If you would like to suggest additional topics, you may do so through typing in the dialog box on your screen. We will incorporate these suggestions in future polls as we did with wildlife management and health effects on this poll. You may ask questions or make comments at any time through typing in your dialog box. Each webinar will be recorded and a brief PDF summary will be produced and posted on the United Drought portal, drought.gov, in the Southern Plains section. We will put up a list of resources, including these links again at the end of the presentation. I will now turn it over to our first presenter, Brian Fuchs, climatologist from the National Drought Mitigation Center, for an overview of drought conditions and outlook. He will be followed by Mark Svoboda, Monitoring Program Area Leader from the National Drought Mitigation Center, who will give an overview of how a flash drought develops. Martha Anderson from the Hydrology and Remote Sensing Laboratory, USDA-Agricultural Research Service in Beltsville, Maryland, will discuss a new evaporative stress index to help give early warning of developing drought conditions. Brian Wardlow, Remote Sensing Specialist and GI Science Program Area Leader from the National Drought Mitigation Center, will then describe VegDRI-A, a Vegetation Drought Response Index. Pat Ganan, Missouri State Climatologist, will then show the difficulties in detecting developing drought in Missouri as they made a transition from a very wet spring to a very hot, dry summer. So we will now begin with Brian and then move into our other presenters.
Okay, good morning, everyone. Again, Brian Fuchs here at the National Drought Mitigation Center, and a quick update of current conditions and what we can expect over the next couple weeks. Up first is the Drought Monitor release from this morning, showing the current drought status for the United States. Over the last week, we did see some improvements in some regions and then some degradation and some introduction of some dry conditions into others. And on the next slide, we look at the southern region as a close-up, and we can see on the statistical table to the left, there was a slight improvement to the overall drought intensities through the region with some rain events that did come through. It is nice to see these improvements, even as subtle as they are, as the last year definitely has been one of the driest on record for the region. If we go through the next slide, we see the conditions for the western U.S., and that does include Arizona, New Mexico, There was no change this week in that region. And if you look at that table off to the left of the map again, you can really see from where we were a year ago to currently, where last year at this time, really not much as far as drought. Only 6% of that region was in drought a year ago compared to 18% right now. And a year ago, there was no D3 or D4 present on the map. So overall for the country this week, we did see some additional drought for the entire United States, and mostly in the Midwestern regions and into the Southeast, and did see some slight improvement to the overall intensity status on the U.S. Drought Monitor for the southern region, and really no change in the western U.S. So the next slide. Over the next 5 days, you can really see the focus of precipitation in the upper right-hand slide is going to be on the eastern third of the country. Down in the Florida Peninsula, you can see some models are showing that Tropical Storm Rena may come out of the Caribbean and maybe go towards southern Florida, so we're going to have to keep our eye on that. It does look like the southern plains have some opportunities for some rain events, but they are going to be light in nature, with the predictions of less than an inch, pretty much standard for the areas that are going to receive precipitation. In the lower left, you can see the temperatures over this time frame, pretty much above normal for the western half of the country and slightly below normal for the eastern half. So you can see where the weather-making opportunities are going to decrease temperatures with the rain over the east and warmer temperatures over the west. Next slide. For the 8 to 14-day outlook, pretty much what we've been seeing so far this summer, this fall, in that temperatures are remaining above normal and precipitation chances below normal, especially through the plains and southern areas of the country. We do see some indications at the 8 to 14-day period of a storm system coming into the Pacific Northwest. Again, that's associated with below normal temperatures and increased rainfall chances. And we'll see how those storms, as they start pushing their way through the Pacific Northwest this time of year, how they will start impacting some of the drought regions of the plains, and will some of that moisture and those storm systems make it down into the southern U.S. Next slide. Again, here is a seasonal outlook here, starting with November and going for the months of November, December, and January on the bottom two frames of the slide. And I did highlight for the seasonal outlook of November through January that the area that's being impacted right now with the significant drought situation in the southern plains, I have that circled. And realistically, through the winter months with La Nina developing and impacting the United States, we are definitely seeing the La Nina signal of drier and warmer conditions through the southern tier of the United States. With that in mind, it's going to be really hard-pressed to make any substantial improvements to the drought situation that we currently see. Next slide. And this is shown really well with the seasonal drought outlook. You can see the areas in red is where we have drought persisting through this time frame, and the areas in yellow is where we anticipate drought development through this time frame. This lines up really well with La Nina conditions, and we're really going to have to see, again, as these storm systems move through, will that La Nina influence be strong enough to indeed change the storm tracks and pushing systems out of this region. But as I said earlier, it does not look favorable for a great improvement to the drought situation through the winter months. Next slide. The featured product for this week is what I want to talk about here is, did you know that there are more monitoring tools being made available using gridded data and provided using the USDA percentiles? And what this is saying is that as a drought monitor author, we are having more tools made available to us using gridded data sets that are on a finer scale than some of the station-based data sets that we're using right now to monitor drought around the United States. And just to give a taste of this, I have selected 3 examples of products that are doing this and how they were set up with the U.S. Drought Monitor in mind, hoping that the authors putting together the products would be using them, and indeed we have. And so I'm going to briefly talk about the NLDAS products, some products coming out of the University of Washington, and then a product also coming out of the State Climate Office in Texas that John Nielsen Gammon's group is working on. So next slide. The NLDAS soil moisture products use modeled and in situ data to put out an idea of what soil moisture conditions are around the country. What I have right now showing is the ensemble mean for the U.S., and in the circles I'm showing the U.S. drought monitor percentiles have been highlighted in these products because they are going along with the methodology and the idea of the drought intensity categories for the U.S. drought monitor being dictated in these products. And so this is just an example of, on the left, soil moisture percentiles for the total column, and then on the right-hand side for the first meter of the soil moisture. And you can see that these areas are really standing out in the southern plains, New Mexico, and some of the developing drought areas through the Midwest as well are being picked up quite well by this product. Again, the link is provided below if you want to go and explore these products, or we can talk about them further during the question and answer period. Next slide. The University of Washington is doing something similar with the Vivid soil moisture product. And again, they developed this with the U.S. Drought Monitor in mind, as they too do the U.S. Drought Monitor percentiles right on their products, and those again are highlighted. And you can see that this not only covers the United States but into Mexico. And on the right-hand side, they do have some regional views that have the county overlays and are very useful when we are looking at some of the fine-scale drought conditions that have developed around the country. 10 years ago when the Drought Monitor developed, none of this was available to us. So this is a good example of how people are out there developing products for monitoring drought that the authors then can use, and it's on a very fine scale compared to some of the data sets that were around when the Drought Monitor was started. Next slide. And the last one I'm going to highlight is the precipitation gridded product out of the State Climate Office in Texas. And what this is doing, it's using a 4-kilometer grid that is developed with the radar estimated precipitation products from the National Weather Service to develop the standardized precipitation index products that are used to monitor drought. And down at the Texas State Climate Office, they've done this, and they've also kept in mind the U.S. Drought Monitor, which I've highlighted on the right-hand side, with the intensity levels that they have dictated on their product. But as you can see, with this 4-kilometer gridded product, you can really have some fine-scale attributes being shown on this product that we, in turn, can use to monitor drought in Texas. And we really appreciated the work that John Nielsen Gammon and his group have done to put this out there. I think that's my last slide. So just a quick overview of current conditions, where we're going in the next few weeks, and then some of these newer products that have been made available to us on a gridded scale that's much finer than what we have had in the past as far as data goes.
All right, good morning, everybody. Mark here. Just want to go over a few primer slides, if you will. Then I'm going to turn it over to a couple of my colleagues that are really working on the ground and developing products that can help us address things like evapotranspiration, flash drought, that will eventually, and some of these are already making their way into the drought monitor process. Next slide. So what do we mean by flash drought? I'm sure a lot of you have heard of flash flooding, of course. When it comes to drought, though, you typically think of a very slow onset type of disaster. And I'm sure you've heard also of the real estate adage of location, location, location. And when it comes down to drought, outside of the fact that all droughts are very local, I think it really comes down to timing. And as you'll see on the couple of products that will be illustrated here in just a minute with Martha and Brian, that evapotranspiration really does vary regionally and seasonally. And so can we capture those and incorporate those into the drought monitor on a weekly basis? And so some of the products they're developing, I think, could really bridge that gap in helping us do that. So the onset of the timing obviously is very critical, as is where you are in the stage of growth of any particular vegetation, whether you're out there relying on pasture or whether whether you've planted row crops. So this all comes into play in trying to assess the effects of drought, the effects of temperature and soil moisture on drought. So therefore, the preceding conditions are very important. How did we go in to the growing season from the off-season recharge period and recharging that profile to 100% if possible. Obviously, we know a lot of places we don't do that every year as we go into the Midwest with more receptive, deeper soils that we can have a nice security blanket come July or August when it's more likely that the tap will shut off. We also gauge droughts using this equation of the magnitude of a drought is equal to the intensity of it times the duration. And where you'll see flash drought come into play is that we can see a very rapid onset event, so a very intense event over a very short time frame would lend itself to this equation of intensity times duration both being intense and short-lived, perhaps. Not always the case, but certainly they can be short-lived, and we'll have what I term a loose definition at the end of these slides. And then also the drought really does exacerbate the problems of VT. If you think about it, when we have droughts, we have persistent high pressure, we have less cloud cover, more sunshine or solar radiation. Typically, you're going to see more wind in that situation, and the likely development of heat waves as this particular region is sort of moisture-starved, if you will. Next slide. During these times, we also see a very below normal relative humidity type readings, which can lend themselves, obviously, to wildfire or forest fire risk being enhanced. And so all of this adds up to a very higher demand on the soil moisture reserves, which can lead to a couple things. Either the plants are going to shut down and quit transpiring, whether they're conserving to make it through it. If it continues on long enough, it could lead to actual the dying of the vegetation. And that, again, depends on the type of vegetation cover, if it's a drought-tolerant shrub versus a very non-tolerant crop versus grasses, etc. They have different root system depths to cope with that. And then also, how does this play a role on evaporation from open water, soil, and snowpack? The other last thing we've looked at being of particular relevance of one of the impacts of these type of events is higher nighttime minimum temperatures, which are also very stressful on both livestock and crops. So there's really no recovery period at night, which adds stress to both of these factors. Next slide. So, in sort of wrapping up sort of the context behind what we kind of mean by flash drought, we first used the term loosely back in 2000, and I think at least Mark Schaefer and Gary McManus there in Oklahoma can probably recall that the late onset, very rapid onset drought in the southern plains in 2000, in particular parts of Oklahoma, where this really came on fast at the end of the growing season. So based on that, I think we used it in one of the narratives for the Drought Monitor at the time, very early in its infancy, and then thereafter kind of caught on quite a bit through the media in 2000 and 2001. So I've started sort of a loose term definition, as there is no one literature source to cite for this, but loosely calling it a relatively rapid onset extreme event, coupling precipitation deficits with intense heat and winds that occur during a critical phenological stage in the growing season, often impacting vegetation, crops, livestock, and can also increase wildfire outbreaks. So as I mentioned in parentheses, there are a couple places. One is that they can come on very fast and also subside, but have major impacts if it's during a critical stage of a particular crop, for example. It doesn't have to last for seasons or years like it might to draw down water supply. So again, how drought affects you is going to play a role in that. But I think what all of this illustrates is how complicated and integrated this really is. And it really illustrates the need for these new sort of what I call new breed of hybrid or composite indicators, gridded indicators of various aspects of the hydrologic cycle that we need to do a better job of integrating into a drought early warning system and the drought monitor in particular. So I just want to show three products here to end up. The next slide shows this kind of encapsulates, I guess, from the June through August period of this past summer, where you really saw the heat entrenched in the southern plains and on the periphery into northern Kansas, eastern Colorado, New Mexico, Missouri, Arkansas, and Louisiana. So you can really see that with the core of that being anywhere from, even 10 degrees or more above normal over a long sustained period. Next slide shows that the very core of 100-degree days, not 90 or 95-degree days, but rather 100-degree days, was very intense. what you would typically associate with the desert, as you see there in Arizona and in California. We were seeing in Texas and Oklahoma the most in particular, followed by New Mexico. But paying attention to what we're calling flash drought is sort of the reds and the oranges, and even the yellows on the periphery on the northern and eastern and western flanks of this drought. That's where we were seeing a real issue kind of came up this year in the drought monitor was what role is temperature playing in drought versus the lack of precipitation in and of itself. So very hard sometimes to separate and play those out. That's where it becomes very important to incorporate more and more data like what you're going to hear about next. And my last slide shows sort of a modeled what the winds were doing, and you can see how these winds were modeled as much greater than normal. Again, for some of those factors we talked about earlier in the ET cycle, that leads to those pressure differences, that leads to those winds. You can see some really, that bright red blob there in the southern U.S., south central U.S. that was a result of, I believe, a lot of that source region drought that we've shown in the previous slides between Brian and myself. Okay, so with that, we're going to turn it over to Martha to go more into sort of the ET side of things.
Okay, well, thanks for having me. I think some of the text in the boxes got converted from white to black, so you may see some strange artifacts in this PowerPoint. But I've been working for several years now with people at USDA and NOAA on developing some multi-scale, multi-sensor thermal remote sensing products for evapotranspiration. I'm talking about how we can use these ET maps potentially for monitoring drought impacts. Next slide, please. So we can make drought indicators out of almost any component of the hydrologic budget. If we look at anomalies and precipitation, of course, we're looking at water supply. Soil moisture, groundwater tell us about storage changes, and the ET component is really related to water use at the landscape scale. Under normal circumstances, we'd probably expect anomalies in these different quantities to be pretty well correlated, maybe with some time lag. So in these cases, the drought patterns are driven mostly by precipitation, and something like SPI would be a pretty good measure of drought impacts that are observed on the ground. However, more interesting cases are when these indicators become kind of unsynchronized, like when the SPI is telling us that the rainfall has been relatively normal, and yet the crops are starting to fail because of the inadequate soil moisture. And this is the flash drought situation that we are talking about today, and seems to be related to extended periods of elevated water use for ET. Next slide, please. Now, the primary factors that are driving the ET are shown in this slide in yellow. The climatic factors that determine the potential ET we would expect under non-moisture limiting conditions include net radiation, or the energy input from the sun and the atmosphere. We have vapor pressure deficit, air temperature, which tells us how desiccating the overlying air mass is, and of course the wind speed that drives the turbulence and transports the water vapor from the surface up into the atmosphere. Now, actual ET can be downregulated from this potential rate if soil moisture becomes a limiting condition, and serving to reduce both E, the direct evaporation of water off the soil surface, and T, the transpiration component of ET as the vegetation becomes more and more stressed. So a stretch of unusually hot, dry, sunny, and windy days can rapidly serve to deplete the soil moisture pool and lead to poor vegetation conditions, even when the rainfall is more or less normal. Because this T component is so tightly physiologically coupled to carbon uptake, true photosynthesis in the opposite direction into the plant, ET is a really good indicator of the conditions that the plants are actually experiencing on the ground, because it kind of incorporates all these different microclimate drivers. Next slide, please. So the thermal-based remote sensing approach for mapping ET that we've developed, it includes all these micro-meteorological drivers, and so theoretically should be able to capture these flash drought events. The primary remote sensing input to the model is the land surface temperature, which we kind of use as a proxy measure of the surface moisture status, both the soil moisture and the vegetation cover. We know dry soils and stressed vegetation both can contribute to an elevated land surface temperature signal, and we can detect those elevated temperatures from satellites that are observing in the thermal wave bands. Now, in this remote sensing approach, the surface temperature is actually used to constrain estimates of sensible heat flux off the land surface, and then ET, or latent heat, is computed as a residual to the overall energy budget. So very importantly, precipitation is not an input to this modeling system. Instead, we're looking at variations in surface temperature. So it's really a very independent drought indicator compared to most of the precip-based indices that we're more used to. Next slide, please. And this is just an example of multi-scale ET maps that we can generate with this modeling system, going from the global scale to continental using thermal data from the geostationary weather satellites like GOES over the U.S. And then we can make finer scale maps using systems like MODIS or Landsat if we actually want to see ET distributions at the scales of individual agricultural fields. Next slide, please. Let's see. Can you hit again? Oh, there we go. So if we're to develop a drought index out of these ET maps, we compute anomalies in the ratio of actual to potential ET. And normalizing by PET actually helps us to remove some of the drivers on ET that are more related to cloud cover and radiation load from the moisture drivers that we're more interested in when we're talking about drought. So we compute standardized anomalies in this ratio, and we call that the evaporative stress index, or ESI. Next slide. Here I'm comparing this thermal-based ET drought index under the second column, ESI, with anomalies in drought monitor classifications and 3 precip-based indices, 3-month SPI, soil moisture, and ET out of the NLS NOAA modeling system. You can see if you compare these on a year-to-year basis, the thermal remote sensing really reproduces the patterns we're seeing in the precipitation deficits pretty well, with the advantage that we use no precip data to make those maps, so they're very independent and also very portable to other parts of the world where we don't have as good precip data as we have here in the U.S. Next slide, please. So this got a little weird, but this is looking in more detail at monthly evolution in this evaporative stress index, 1 month, 3 month composites compared to USDM and precip patterns, going from late 2010 into 2011. To date, we've been focusing mostly on the growing season. We have a little gap there between April and October, but we're going to be filling that in the near future. Again, pretty good spatial and temporal correspondence with the drought classifications. Again, bearing in mind there was no precip data used in the creation of this particular index. You can see the band of drought in late 2010 that went kind of from Indiana down to East Texas, which then kind of, I guess, morphed into the scale drought in the south central U.S. in 2011. In 2011, we can see some, if you can, I don't know, they might be kind of small, but there are some short-term features in the ESI that correspond with features in the drought monitor. For example, in July of 2011, see some kind of month time scale dry conditions in Pennsylvania and New York that the ESI is picking up. And then in August, there is a band of dry from Iowa down towards Florida, corresponding with a band of lower precip that the surface temperature is picking up. Now, in terms of capturing flash drought, this is something we want to investigate in the next year. Presumably, we would see a short period of elevated positive ET anomalies followed by a rapid decline into strongly negative anomalies. So we'll be looking for those kinds of signatures associated with some of the flash drought events that have occurred in 2011 and 2008, particularly in the south central plains. Next slide. This is just to show we're developing a prototype web service to deliver these maps and in comparison with other precip-based products for easy intercomparison. So thank you. That wraps me up.
Good morning, everyone. This is Brian Wardlow from the National Drought Mitigation Center. And I'll be talking about a tool that we developed, the NDMC, in collaboration with the U.S. Geological Survey and USDA's Risk Management Agency. Development began almost a decade ago, and we've been operational across the U.S. for the past several years. The primary driver of developing this new tool called VegDRI-A was to provide drought-specific information regarding vegetation at a higher spatial resolution, initially to support the U.S. Drought Monitor, but as you'll see later in my slides, that there's a number of new applications emerging using kind of a hybrid-based approach that integrates remote sensing with some other traditional sources of information used for drought monitoring to help us tune in the drought signal. Next slide, please. But to understand VegDRI-A, a good starting point is to look at traditional satellite-based vegetation monitoring that has typically relied upon the use of vegetation indices that combine spectral information from several spectral bands on satellites. The most common of these is the NDVR, the Normalized Difference Vegetation Index, and it's proven to be quite useful to map and monitor vegetation conditions over large areas across time, as illustrated by the time series animation on the right, showing the green up vegetation across North America in the spring, and then kind of the brown up as you see senescence entering late summer and fall. The use of vegetation indices, or VIs, has a couple of advantages. One is they're very simple to calculate, and secondly, research has shown they have a strong relationship with biophysical characteristics of vegetation. Are very good indicators of the cumulative effect of environmental conditions on vegetation conditions. But when looking at the vegetation index data, specifically for drought monitoring, there's a couple of challenges or limitations in only using VI information. And the first is that although it does show an indication of the general state and health of vegetation, it's very difficult to determine in areas showing a stress signal what is the driver of that stress. Is it drought, or is it another cause? Could it be pest infestation or flooding, fire, or even land use, land cover change? And secondly, using VI data, it's very difficult to classify the specific severity of drought conditions on vegetation. Is it a moderate drought condition, or is it extreme? How do you classify that? So with VegDRI-A, we've tried to address these two challenges by combining other information with traditional vegetation index data. So next slide. So what is VegDRI-A? It should be thought of as a hybrid index that integrates three unique types of information. We look at your traditional satellite-based VI information I just talked about as the first component. We combine that with traditional climate-based drought index data, and also consider several environmental characteristics that can influence drought stress on vegetation. This allows us to produce maps that have a spatial resolution of 1 square kilometer that depict drought-related vegetation stress. So we're starting to tune in the characterizing drought-specific impact on vegetation in this tool. Well, the two primary goals, the first I mentioned was being able to provide higher spatial resolution information, initially for the drought monitor, but I think there's other applications that are seeing value in this as we're starting to produce this operationally. And second, we're placing the information on a widely recognized drought classification scheme. We're using a modified version of the Palmer Drought Severity Index scheme to classify drought stress. Next slide. A little bit more about the hybrid approach and how these three basic components work together and helping us tune into the drought signal. For the remote sensing component, you can think of this as our high-resolution input that allows us to get down that 1 kilometer resolution. We use several variables calculated from NDVI data, so we're looking for a stress signal on the satellite information over a given location. We combine that with climate-based information, which provides us the coarser scale representation of dryness across the landscape. We're specifically using SPI and the self-calibrated PDSI to do this. So in the remote sensing, we're looking for a stress signal, and the climate component, we're looking for a dryness signal, helping us focus in on drought areas. And the third is the biophysical. We look at things like land use, land cover, soils information, elevation, and irrigation status, because each of these characteristics can influence climate vegetation interactions and thus the level of drought severity experienced at a given location by vegetation. So next slide. Here's an example of a VegDRI map from this past July over the U.S. In the lower left on that map, you can see the classification scheme we use. We have 3 drought severity classes, and then we have a pre-drought class. You'll also notice there's a gray class called out of season. The out of season class is actually defined from satellite. This is for locations for a given time during the year where the satellite historically has not observed a detectable green vegetation signal. We've added out of season to our maps to avoid any false positive drought signals at the tails of the growing season when there may not be photosynthetically active vegetation. On the right, I have a list of bullets that talks a little bit about our operational progression of VegDRI. We began producing maps across the U.S. On a bi-weekly basis in 2008. We've actually moved to weekly production in the last year and a half, so we actually are producing maps weekly and bi-weekly using different satellite inputs for those. We've also calculated a full historical record of VegDRI across the continental U.S. dating back to 1989. And at the NDMC on our VegDRI website, we have a number of value-added products. In addition to this map, we have change detection and difference maps. We have tabular data summarizing percent area, time series animations, which you'll see here in a second, and a variety of other products. I've included the URLs of a VegDRI website at the NDMC where you can access that information. Then USGS also has a site that's more of a GIS interactive dynamic viewer that allows you to look at both the weekly and bi-weekly information if you're interested in that. Next slide. It's an animation that looks like it's working. This I just wanted to include to show how VegDRI saw the 2010 conditions, particularly in the southern part of the country. I have a red circle showing kind of the area that we being VegDRI here actually saw drought conditions coming on the mid to late summer last year. We saw that it was oriented east of Oklahoma and Texas, primarily in northern Louisiana through southern Arkansas, is where we were seeing a strong signal late in the summer through the early fall. The next slide. This is the 2011 animation. It looks like it started right in the middle of the year. Hopefully it'll loop back around, but I wanted to show you the evolution of drought as detected by VegDRI for this past year. There we go. So we're starting in January now, and you can see the progression. A lot of the area is gray across the country, across January and February, and you see more and more of the country coming into the VegDRI map as we enter the spring. But you can see in VegDRI that early in the year we were detecting a drought signal in April and May. It intensified in western Texas. You start to see more and more maroons coming into the map. In many of those locations, the Texas Panhandle, looking at the values, they were some of the most extreme drought values in our VegDRI classification scheme that we've observed over the last 20-year period. In terms of flash drought, I think the jury's still out on how early we're detecting some of these events, but we do have some plans in play to try to tailor it more toward flash drought events in the near future, as you'll see in a couple of other slides. So next slide, please. So who's using VegDRI? I just wanted to give you an example of who's beginning to look at this for their drought monitoring activities. I mentioned the USDM authors are one of them, but several states and the National Weather Service are also they're monitoring. We're also having a number of other applications that are emerging, looking at the influence of fire and how is that depicted in VegDRI, also some ecological studies. But since we've only been operational for the U.S. since 2008, I think the number of users and applications is just starting to emerge. But people are starting to use this in addition to the USDM. Next slide, please. And then lastly, I just wanted to wrap up what's next for VegDRI. Our modeling structure allows us to incorporate new variables. So we're looking at some of these new remote sensing inputs that are becoming available and trying to integrate those in a testing phase that we'd like to start the next year to see if we can try to tailor a product that's more applicable to detect flash drought. Currently, we have very little information on temperature in our VegDRI models, so we are looking at things like ET, looking at the evaporative stress index that Martha just talked about as an added variable in our models. We're looking at remotely sensed soil moisture. That's that middle map on the right, looking at that as an added variable. And then also, Brian talked about the work that they're doing at Texas A&M. We'd like to see a gridded climatology, possibly an SPI at a higher spatial resolution to be able to give us a higher resolution climate input as well. And on the left, you'll see a graphic there that really, I think, remote sensing is starting to mature, where there's a number of tools estimating different environmental components relevant to drought that can be estimated from satellite. And I just listed a few of those on there, and I think you'll see more and more of these satellite-based tools estimating these type of variables coming online for drought monitoring in the near future. So with that, that's all I have, and I guess I'll turn it over to Pat next. Thank you.
Hello, this is Pat Ganan. I'm the Missouri State climatologist. I appreciate the excellent comments and the topic for today's session. I think it's been a classic flash drought with according to the definition that Mark Svoboda gave. It was just exactly what happened over parts of southwestern and west central Missouri this past summer. We had a situation in that part of the state where I've been in Missouri for 23 years, and it's the first time I've seen the drought emerge so quickly across the state. And it generally, in my opinion, it was a wake-up call for me and others in regards to this drought that evolved. Despite a very wet spring, all the way through May across southwestern Missouri, we had a rapid onset of drought due to a combination of high temperatures and below normal rainfall that occurred in June and July. And I am putting emphasis on the high temperature scenario that emerged in June. It was, and continued through July, it was our hottest summer across southwestern, west central Missouri since 1980, and we began to see significant agricultural impacts occurring across this area. Despite precipitation that was below normal, but not terribly below normal, it was those high temperatures that really cranked up the ET rates in June and July that led to this rapid drought condition evolving. And another thing, I don't know if it's taken into consideration, but southwestern Missouri has very shallow soils. And so there is a vulnerability to entering a drought condition and the severity and magnitude on how fast that can emerge. And indeed, that was the case across that part of the state. And in hindsight, I was looking at some of the impacts. I got some impacts from extension agents who reside in the areas of southwestern Missouri and some west central sections of the state. And already in mid-July, earlier this year, there were some reports that producers were giving up on the corn and beginning to green chop it or even bale it, as well as the soybeans were very short. They were starting to stress out. Pastures were burnt up. And yet, even though this was occurring, the July 19th drought monitor map was indicating no level of drought whatsoever across some of these counties. And so when I reflect back and look at the situation that emerged, it probably would have been prudent perhaps to put a severe or D2 drought condition as early as maybe perhaps 5 to 6, even 7 weeks earlier than what actually was depicted in some of these counties, as early as mid-July, whereas it didn't occur until early September, where some of these counties were put into a D2 condition. So that's just something I wanted to put on the table. I think another issue in regard to this drought that emerged so quickly across southwestern Missouri really puts emphasis on the valuable information that can come out from an area where people are being impacted, people who are living in those counties. And I was amazed that there wasn't a lot of impacts coming through the Drought Impact Reporter, and that would have been a great resource if the people were aware of the Drought Impact Reporter to use that sort of resource to get their impacts through them. And I think I rely a lot on extension folks who provide some good information, but I think the Farm Service Agency, I think, could be a good resource. I had to send a lot of information on how to use the Drought Impact Reporter, how to get people involved, to some of the FSA agents who were in southwestern Missouri because they were unaware of this tool to use to provide this information that was coming from their impacted area. And here in Missouri, we have 9 crop reporting districts, and each of the districts have a divisional director with the Farm Service Agency. And perhaps we could bring awareness to this, but give some sort of learning session or educational session about the drought impact reporter to the divisional directors, who then could share that within their crop reporting districts. Mark, I submitted to you earlier a news release that we did on the drought impact reporter, and it's free for anybody to look at, just to get the word out and the awareness about how to use this tool and the valuable input that can go into the drought monitor authors in making the decisions on depicting drought across the country.
Okay, well, thank you.
Thanks, Pat, for that, by the way. Thanks.
Okay, here's this is Dave Dubois from New Mexico, the state climatologist, and I just want to give a real brief update since our last meeting on precip. So go to the next slide. I just want to show some, just to look at the precipitation aspect in New Mexico. This is calendar year map. On the right is the percent of average precip. So nothing really new. I've been looking mainly at the southeast part of the state. There's been some improvement in the northwest, and as we saw earlier in the presentation, there was some. Actually, there was white in the drought monitor map. There was no. They were free from some drought, but as you go further toward the southeast, it looks very similar. On the right of this slide, I was just showing some of the worst. This is a query from the cooperative station database, and just showing some of the stations that are suffering the most, like Hobbs and Jowl. They're in the less than 10% in Hobbs. This doesn't include the rain from last night. I know I was looking at the Cocorage observations this morning, and it looks like most of the stations got at least 0.3 to 0.5 inches in the southeast. So that helps a little bit, but if you look in the middle number column, the departures over the calendar year are more than 10 inches, and like Hobbs is like 16 inches below normal. So even if just this half inch would really make a big difference in the precip. So if you go to the next slide. This is just looking at October, from 1st of October to about the 25th. I did a query yesterday, and same type of plot showing what it looks like this month. So same type of thing, where we've got about an inch of rain departure up in the southeast. And this doesn't count the 0.3 to 0.5 inch. So that helps a little bit, but overall, because most of the sites you get around inch and a quarter, inch and a half in the southeast corner of the state for the month of October, based on the long-term normal. So we did see a little bit of snow in the mountains, especially if you go further in northern New Mexico. There was about 2 inches of snow in Tucumcari this morning, and as you go further up toward the Colorado border, it's more like around a foot of snow in the up north. So there's some improvement in the north, but in the southeast, that's where our problem remains. So that'll about do it for New Mexico.
Thank you. It's always a pleasure to give a drought update as it's raining, and it is raining in Oklahoma, as we see from our first slide. This is from the Oklahoma MESNet rainfall totals with the radar estimated totals from the River Forecast Center in Tulsa. We see basically a half inch to over an inch in a wide swath from southwest Oklahoma over through east central Oklahoma. Now, this isn't a huge rainfall, but if you add that to the rainfalls we've had recently, including one last Saturday on the next slide, you can see just in the last 30 days we've had really good rainfalls up and down the I-35 corridor in central Oklahoma and spreading out from there. 3 to 5 inches, with some local amounts approaching 7 inches of rainfall. So as you see from the next slide, that's pretty good rainfall for just October, up to close to 200% of normal. Now, the rainfall events we've had over the last couple of weeks aren't huge, but we have to remember each one of those puts another chink in this drought's armor. So when we get these future rainfalls, it will allow more relief, and those will be reflected on future drought monitor updates. And remember, this rainfall that we are receiving goes into the water bank, and it's stored over the winter months. So if we do happen to be in severe drought conditions as we go into the spring, this will be there available for agriculture to use. as they go forward into the warm months. So just a quick update from Oklahoma. It's good news today with a little bit of drought reduction going on.
Thank you, everybody. We have a couple of other state climatologists on the line. I didn't have any indication they wanted to add anything, but just kind of give an opportunity to chime in here if we do. Okay. We'll now open it up to questions and comments that you've posted. We've got a couple of things up there. First of all, for those able, we invite you to stay on the line to continue the conversation. You can post questions through the dialog box, and we'll relay them here to the presenters. We will leave the list of resources up there on the screen. As a reminder, the presentation materials will be posted to the Drought portal in the Southern Plains section, and a 2-page PDF summary of this will be prepared and posted early next week. I would also like to mention that Skip is now on Facebook, and these PDF summaries will be posted there as well. So going to some of the questions we have. First of all, John Gammon wanted to point out earlier that when looking at the 5-day precipitation forecast in the earlier section, that much of the outlook, even though it was updated this morning, is including the precipitation that's currently falling across Oklahoma and North Texas. So those areas that showed about a ½ inch to an inch of rainfall, it's really coming with this system, and maybe not so much another system that's on its heels. Eric Hunt up in Nebraska had an interesting point that from some of the studies up there in eastern Nebraska that showed that the depletion of deeper depths of the soil profile is causing significant reductions in ET. And I was just wondering if maybe Martha or Brian or Mark have any comment about are we able to take that deeper ET into account with some of these products that you've shown?
Well, the thermal remote sensing, where you have vegetation, the roots of the vegetation are kind of serving as a probe of moisture conditions deeper in the soil profile. So we feel like and comparisons with modeled soil moisture in the root zone and these soil moisture estimates we can infer from the ET over PET maps, we feel like we do have some sensitivity to root zone moisture in the thermal wave bands. Microwave soil moisture retrievals are sensitive to moisture conditions more in the top kind of couple centimeters of the soil profile. Don't get quite as deep without some additional modeling.
And I would just add from a terminology standpoint, many of you, this is Mark Svoboda here at the National Drought Mitigation Center, when we speak about droughts feeding on themselves, when you've got a situation that it's persisted long enough to basically suck the soil moisture dry and gets into those deep soil moisture depletion, when you've done that, there's really no more moisture in that region. The sponge is dry. So that's when a drought can really just sit there and you've got high pressure. The plants have shut down transpiration. You've got very low soil moisture to suck out of the soil. You don't have any moisture coming into the atmosphere at that point.
I'd also like to add to that, one of the challenges when we're looking for recovery is there's very little data at those kinds of depths. And most of the tools we have are geared towards the upper levels that we can measure directly or remotely, or else surface-based data. So trying to understand how rainfall is going first to recharge some of those deeper depths before you'll start seeing the response in the runoff, for example, and refilling lakes. How big of an event is needed? It's an area that we do need to do quite a bit more work. So appreciate the comment. I have a comment from WFO Lubbock there. How are soil moisture maps derived from direct observations, calculations, from other observed parameters, or remote sensing? Any experts on the soil moisture maps that are out there? Maybe Brian?
Yeah, basically all the above. It seems like the people that are working in this are using a combination of both modeled and observed data sets, and where soil moisture is being observed, that is being fed right into their models as well. So it is a combination of all the above. And for those states that do have their own networks at the state level, and they have soil moisture probes. They also are providing products that are relative to that region that we in turn can use in creating the drought monitor.
Okay. All right. We also, Eric Hunt chimes in again, a flash drought in 2003 here caused a reduction of over 100 millimeters in measured ET in rain-fed corn compared to nearby irrigated corn. Yields were reduced by over 90 bushels per acre in the rainfall site compared to the, the irrigated site. So I think Martha had mentioned kind of or VegDRI-A, I guess maybe it was Brian had mentioned the challenge of the irrigated areas and taking the land use kind of land cover applications into effect, and I think that's a great example of it. So I think it looks like that's all the questions we have. There's a comment asking if these are recorded. We do have them recorded. They tend to be very large files we found. So we post the PowerPoint slides will be on the Drought portal, the NIDIS Drought portal in the Southern Plains section. We get those up there within the next day or two. And there will be a PDF summary. If somebody really wants to be able to listen to the webinars as recorded, please just send us an email and we'll see if we can find a way to make it available to you. So are there any other comments from any of our presenters or anyone on the line? Okay, I guess that will conclude this third one. The next webinar will be on November 10th, and the topic will be determined. We're going to look at the poll results. We've started looking at some of the ones that were indicated as very favorable topics in previous ones. We've already started working on trying to line up presenters. So we will get that information out to you shortly, along with the summary, and we will also circulate the press release on how to report drought impacts using the drought impact reporter. We'll circulate that as well, because even though it's geared towards Missouri, I think the information in there is excellent on really anybody and the importance of getting those observations, the local impacts and reports into us to help us through this process. So I appreciate everybody, and have a good remainder of the week, and we'll see you on November 10th. Thank you.